Today we're going to talk about TDD fundamentals in C#. Not that the fundamentals are any different in other languages, just C# is our reference language, and I'd imagine most of today's content could quite easily have dropped to C#, but the exercises are specifically focused around C# that we'll be going through. So quickly, what are we going to discuss in the video? Its purpose, why TDD, the value proposition, why use TDD, a Gears model. It's a model I've put together kind of to help me, I guess, better frame an approach to doing TDD, just kind of rather than just taking the red-green refactor cycle and a few of the other things, trying to think, kind of how we can vary our approach to TDD. You're not always going to be doing the real simple things. You're not always going to be doing the really complex things. It's just a way to, I think, more accurately approach TDD as a practice and kind of keep a larger frame of reference than just going, oh, it's these simple principles and I go red-green and, things pass. There's a little bit more thought to it. We'll talk about that in more detail. And TDD principles. There's a lot of key principles that drive the process. Lots of things that we should touch on at the very least, and kind of add a bit more exposure to the depth of TDD. So why do we need TDD? Well, as the image to the side there shows, TDD's all about all code being guilty until proven innocent. What does that really mean? Well, that means generally, we make a lot of assumptions when we write code. There's a lot of accidental complexity that creeps in just because we're trying to solve the problem. And accidental complexity is the extra complexity we add that's not core to the problem domain. We avoid mental overloading, trying to model the entire system at once. Often how we tend to tackle software in a non-TDD approach is to go, oh, okay, cool. I think I know what to do. I'm just going to bash some code out, keep tweaking it till it works. And in doing so, probably miss some big moving parts. Maybe not. Maybe only some small moving parts. Reduce the fear to make changes. This is a big one for me. Regardless of the actual value in, having a test suite, it's about being able to refactor at the end of the day. And often we're afraid of making changes because we're not sure, are we going to break something? Tests creates a better space for us to remove that fear. And by removing fear, we actually increase our productivity. Fear tends to lower IQs, which oddly enough makes us a bit less effective at what we're doing. And it creates a natural rhythm. Every developer kind of has their own workflow or way of doing things, and I like the TDD rhythm. It just seems like a real natural cadence that facilitates short feedback loops, getting that insight, carrying on and moving to the next problem at hand. So really, we're trying to decompose large problems into small little experiments, and to write theories around those experiments in the form of tests, and to see what we need to do to get those experiments to be true by making them green, and often trying to do the simplest thing to get there. And of course, obviously, going through those small incremental refactors afterwards. The other day, someone asked me the question of, it's all great and well to talk about, craftsmanship and all this, but how do you really find the time to refactor? And my answer was through the use of TDD, or at least the TDD thinking. That methodology that comes from thinking that way, of taking small steps and getting it to a good state, and then taking and doing those small little refactors everywhere along the lines. My experience has been typically if we don't always kind of take and pay attention to what we're doing and try to improve it, we're going to end up in a situation where 3, 5, 10 years down the road, we throw our hands up in the air, say the thing's a mess and it needs to be rewritten. It's no different than keeping your house clean. If you don't clean it, it's going to get dirtier and dirtier and dirtier, and then when you do get around to cleaning it, it's going to feel like a monumental task. Not that you abandon your house and all your stuff, but it's going to get to the point where it's going to take hours or days potentially to get it to the state where it looks like it did when you first moved in. So normal development flow, we're kind of used to writing the production code, and if we have to, writing some tests maybe. And this generally forces us to solve a problem at the macro scale. So, lots of parts we have to hold in our head. We got to all kind of make it make sense, which is self-defeating because at the end of the day, our working memory only allows us to hold about 5 to 7 items concurrently, which means we're constantly swapping things in and out, which once again means we're actually not effectively using our biology to our advantage. TDD, I'm not saying you're only ever going to have up to 7 things, but you're going to have far fewer things you're trying to keep in your working memory as you work through that portion of the problem. An example of a normal development workflow, you maybe write some more code. As you can see over on the left, I've got the little snippets of code kind of feeding into more code, and at the end, maybe you write a test. And that test is probably going to cover everything you just written. Maybe you write a couple, because you're going to look at the happy path and the sad path and maybe some of the other weird things that can happen. But you're going to try to exercise as much code as possible at the end if you do write tests. Which, you're really just then kind of trying to take an approach to say, hey, look, I've done my due diligence, pretty sure this thing works the way it should. Good luck trying to debug any major issues that come back with the test I've written, but, for now I'm happy. I'm going to hand it off. The graphic running more in the middle of the screen elaborates on this a bit more. We write code, we run the app. It works or it doesn't. So either I'm finished or I'm not. If I'm finished, I might refactor the code. If it breaks, I'll probably revert, commit it, and go home. It's probably been a long day. If I'm really feeling brave and it works, I might write a test. And I'll run those tests, and if they fail, I'll go back and write more code and kind of work my way through that whole long feedback loop again. If it passes, I may write another test or two. Who knows? It really depends on kind of where I am and what the expectations are. Not to say that you should be aiming for coverage or any kind of crazy number like that, because those things are easy to game. They truly are. Some of the problems with a traditional development workflow, there's no specific time to roll your learning about the problem into the solution. There's no natural cadence that allows you to do that. You're always kind of chasing speed, which really, sometimes you need to slow down to speed up. And I think development often is one of those cases where if we just go a little slower and think about the problem just a little bit more as we're working through it, we probably would write less code and write better code. Well, that's been my experience at least. Lack of quick feedback about work quality. So, we're one of those professions where in the traditional sense, we write it, we hand it off to QA, wait a day or a week to say, hey, this is broken, or everything's good, which seems kind of ludicrous. Not to say that there isn't a role for QA, but, realistically, we should be responsible enough to have that level of professionalism to ensure quality in our work. And I don't mean firing up the app and spending hours bashing away through various scenarios. Why not automate it with a test? Some people believe that upfront planning will solve the quality issue. If we just get waterfall right, if we can just do all the planning, it'll all work out. Software is not like a building. It's really easy to make changes in software, and it's really hard to make changes in a building. So planning's important, but understand that no battle plan survives contact with the enemy. So in this case, no grandiose plan that you put together is actually going to survive contact with a client or a stakeholder. There's going to be changes. There's going to be a need to make your code malleable. That's really what we're going for, is a high level of malleability. And of course, as I've mentioned, too afraid to breaking things to really refactor and improve code quality. TDD dev, well, we kind of invert things. We write a test first, then we write just enough production code to make it pass. And that's really a key point. If you write a test, write some code to make it pass, you write another test, and that test passes, you very much in the scenario where you've written way too much production code in the first for the first test. You should really go back, comment out things, or make it so that only that first test passes, come back, and have a failing test. The reason we always want to start with a red test is that's how we test our tests. If we never see them fail and they're always passing, we don't know that they're actually ever going to fail. And I've had this in my earlier days of TDD where I wrote tests and I'm like, yeah, that scenario's fine. Of course it's going to pass. And then lo and behold, 6 months later, there's a bug right there in the system. Right there where that test was always passing. And, turns out there was never really a scenario that was going to make it fail. So always make sure you have a red test. And really it forces us to problem solve one step at a time. And this may be what feels awkward or unnatural about TDD is, yeah, you still need to be aware of the larger context, but you're only focusing on just getting those next steps out. Often it really results in less code quicker at a higher quality. I say often because there's no golden solution or perfect way to do this. It is very principle driven and lots of practice to get there. But generally, if we can apply the workflow, do the refactoring, understand the principles that are driving us, we should end up with less code, fewer bugs, and all out the door a lot quicker than if we don't. A TDD dev workflow, off on the left, you can see code flowing into tests, flowing into more code, flowing into more tests. It's a real kind of natural rhythm. You can just see in comparison to the right code first, then test. It's a little more clunky. We're taking big steps, kind of building assumptions on assumptions, hoping when we get to the end of test, pass, and if they don't, then we kind of just bash away at it until it does, versus this more natural cadence of taking small steps. So what do? We write a test, we run the test. Does the test pass? Well, if it does right away, then maybe it's not a very good test. We probably need to look at our implementation, have a few thoughts about what's actually happening there. So let's assume it doesn't pass. We write some code, we run the test. If the test fails, we try a little more code and carry on until we can get the test to pass. If the test is successful, then we refactor the code. And I think this is a really important step, and I'm really going to bring a lot of emphasis to it, is it's red, green, refactor. I like to say red, green, reflect, refactor. So forcing us to actually read our code, slow down and read our code, understand what we've just written. Look for naming and solid principles and all the things that just that little snippet of code we can apply, all these things that make good code too. Refactor, test. If the tests all pass, happy days. If they don't, go back, do a little more refactoring, until we can get it into a good state again. But we're just taking those small steps. We're just moving forward incrementally. So why use TDD? I like to think of there's two really good reasons why I really believe in TDD. Clean code. And I do mean that in kind of the Robert C. Martin sense, and the book, all the kind of principles and guidelines he outlines there. So TDD has that reflect refactor step built in. It provides a natural space in our workflow to apply principles like solid, single level of extraction, improving, iteratively improving the code quality, improving the naming. It also allows us to focus. So focus is really important for developers. I don't think, we often know when to kind of get lost. At least I lose time from time to time. I'll look up and 2 hours have passed. But am I solving the right things with my focus? That's really the problem. There's a reward that kind of is naturally driven through solving that problem. We get a little dopamine hit. And so every time that the test run goes green, we get a little reward. We get a little natural reward. So if we use that mechanism, our own biology in this sense, to drive a positive feedback loop from test to test, we're better utilizing our mental capacity. We're naturally building in a reward mechanism into how we write code. And because of the lack of fear and uncertainty, or at least the reduced fear and uncertainty, once we get comfortable with TDD, because anytime you learn something new, there's always some fear and uncertainty, we start to have a higher IQ because the fear is not pushing it down. It's not trying to kick in some of those more primal systems of fight or flight. And we've got this mechanism that's kind of pulling us forward naturally, test to test to test, making our code of a higher quality if for no other reason other than that we're able to access more of our mental faculties in doing this. Next, I'm going to talk about the TDD Gears model. We'll talk about this more in detail, probably in some later sessions. I just like to kind of introduce all the key theory in the beginning. Typically, if I were to offer this in person, we'd probably spend an hour or two just going through theory. Because this is a little more async, I'm going to cover the theory in brief. It's all in the manual. So I would advise kind of reading through that after watching the video to just kind of fill in any gaps that maybe I've missed in talking through these concepts. See, the idea of TDD gears was kind of modeled after driving a car. You know, when you first start driving a car, you're probably going to go in like first or second gear, kind of a low gear, get a feel for things, start to understand this new machine that you're intending to operate. So each gear represents a degree of adherence to the practices and the scale of thought. Now, when I say adherence to practices, I mean generally in lower gears you're going to be doing simpler things versus the higher gears. And you'll notice, just like a car, there's a reverse gear because, you know, TDD is not a silver bullet. You can get stuck, especially when you're in the higher gears. It's very easy to work yourself into a space where you can't find the next test, or, you know, some other funky, you can't get the test to go green, some other funky kind of problem like that. So principles are used to drive professionalism in our code by shaping the maintainability and the quality, and professionalism must always be present regardless of the problem domain. So basically what I'm saying is there's never an excuse to write really poor code. You know, I understand, you know, it's kind of beauty's in the eye of the beholder here, but, you know, at the end of the day, we should always be striving towards writing the best code we can based on the knowledge we have. So the gears, briefly, we've got low, medium, high, and reverse. So low is about building context, understanding the domain. Medium is about building elegance and good design. So you're probably a little more comfortable in the domain. You're starting to see the concepts. You want to focus a little bit more on the design, not just solving the problem. High, we build structure. We follow existing patterns, potentially a bit of copy and paste because we're just making another version of something that exists in the system. And reverse is about, well, we're struggling to refactor or find the next test. We've got to actually back up a test, comment out the tests we're on, go back a test, and see if we can discover a new test. So now there's some principles and practices. I'm going to cover these in brief, mainly because they exist in the material. So I'm going to just talk about them very shortly. Like I said, it's probably a good idea to go back and read some of the material on this just to get a richer sense of what these are. Someday I may come back and record individual videos for each of these, but if I were to do that all now, I'd probably be talking for at least another hour. That's generally how it works when I do the in-person stuff. So the first one's the 3 laws of TDD. So the 3 laws of TDD, they're quite important. They state you're not allowed to write any production code unless it's to make a failing unit test pass. You're not allowed to write any more of a unit test than is sufficient to fail. And compilation failures are failures. Now that second point's really important. Because you're like, hey, I'm going to start writing a test for code that doesn't exist. What do I do? Good question. So when you write your test and the code that you're trying to write for doesn't exist, you stop. You technically have a test failure. Bring that class into existence, like control enter, I think it is. Get it to create the class. Get it to not talk about compile failures anymore, and carry on filling out the body of your test. And briefly, the body of your test should contain an arrange, an act, and assert structure. Arrange is where we organize the things. Act is the actual exercising the method we want, and the assertion is testing the results. So after we've written just enough of a unit test, then we're not allowed to write any more production code than is sufficient to pass one failing unit test. So write just enough to make it work. Just enough. And driving that whole process is the red-green refactor cycle, or I like to say the red-green reflect and refactor cycle. So we write a test, we run the test fails, we write some code, we run the test. If the test still fails, we write some more code. We kind of repeat that until the test passes. Once the test passes, we read our code. And I do mean actually stop to read your code. Think about your naming. Think about just how you structured it, what concepts are there, how are things put together. Identify some refactorings. I think there's a refactoring reference in the document, so you kind of use that as a guide. Mainly driving out your solid principles, single responsibility first, and then the rest. Refactor your code, run your tests, everything's green, kind of repeat the cycle. It's a really simple cycle at the end of the day. And it's governed by the 3 laws of TDD. So you're like, okay, cool, that's nice. I've got 3 laws and a really simple red-green refactor cycle. How am I meant to approach this? What's the point? Well, there's these thing called green bar patterns. So green bar patterns are, oh gosh, in the book by Kent Beck, TDD by Example. If you don't know, Kent Beck's kind of the father of TDD. In addition to design patterns, he had contributed there in a few other areas. He's I'd say, done a lot of really good work in this industry, even though it is a bit underappreciated at times. So the simplest green bar pattern, if you look in the manual, is the Fecat pattern. It's the most utilized when building context, so this is really the pattern you kind of stick to in that low gear. And it's useful if you don't have examples or the examples are unclear. But if you, and the idea here is to apply the pattern to work in small increments until you find a generalized solution. So basically, you literally start off saying something like, if the value is equal to 3, return fizz, as in the FizzBuzz Karta. If it's these hard-coded kind of cases. Now what you're doing is you're trying to find a more generalized solution there. And one of the things that we really need to keep in mind is the rule of 3. Until we kind of have a sequence of 3, we can't truly identify a pattern. That comes from math. So really work until you have those 3 examples, find the generic solution, refactor out that hard coding into a more algorithmic solution, and go forward from there. Obviously you should only ever refactor when your tests are all green. The sister pattern of Fecat is triangulation. So this is great if you've got 2 or more good examples. What you're trying to do is work with those examples and kind of hone in on the generic implementation. It feels very similar to the Fecat. You start off with hard coding examples in an attempt to find a general solution. You should see a pattern merging after 3 or more. If after 6, I'd say you can't see a pattern in either the Fecat or the triangulation, it's time to hit reverse. You're stuck in the mud. You're not really going to go anywhere. You're probably going to make a mess of your code. So it's time to back up and try a different angle. Try a different example that you have. And when I say back up, don't delete your tests. Just comment them out. They may add value later. Comment them out in any code related to them. Get yourself back to a green state. Always start from a green state in reverse. And work your way there. Often is well with triangulation because you've got 3 cases around a specific equivalence partition. We'll talk about the equivalence partitions and boundaries a bit later, but basically an equivalence partition is any input in that space will always give you the same result. So when you're driving through triangulation, you're going to likely be looking to make test cases, at least initially, because they're kind of in that same, you're going to make test cases. We'll talk about how to use test cases appropriately. They're something to be used rarely. You should not use them as your first go-to. A lot of people, when they do TDD, just put test cases everywhere, which is great because it's easy, but your test should always describe a specific scenario. And if those test cases aren't driving at one really good descriptive sentence, then it's not driving at a specific scenario, and you need to think about making multiple tests. Testing is one of those areas where we actually prefer some level of duplication. And I say some level because there are more advanced techniques we can use to kind of pull out some of that common setup and whatnot. But each test should be a small, readable story at the end of the day. It needs to add all the context without scrolling. If I have to scroll to add context to what's going on, then I likely am writing tests at too coarse a grain, or I'm trying to make reusable components. Then when there's better techniques, test setup and teardown are the devil. Don't ever use them. Like, seriously, don't ever use them. Would prefer to recreate it every time in that test method, and then pull out a method for the common setup if you have to. The next really awesome green bar pattern is one-to-many. So this can be useful when moving from like a single item to a collection. So let's say eventually I need to process a list, and there's going to be some complex internals around that. Don't pass the list right away. You can pass a single instance of that. Worry on just focusing on the specifics of getting that particular thing to save to a database or call an API or whatever it needs to do. So you can kind of lay down the foundations of that internal mechanism and then go to the many. So it's always about solving the problem for the singular and then solving it for the many, because the many adds a different element of complexity that's not necessarily inherent to the core portion of the problem you're solving initially. And if you look in the manual, I've got a few variations, like evolving a public method. What else do I have? Isolating private method complexity. And I've got a TDD here for isolating variables in an algorithm. This is from a couple years ago, this material. I haven't come back to it until just now. So at some point I will update this and go through it. So we've got Fecat, we've got triangulation, we've got one-to-many, and we have the most dangerous pattern next. Because this is everyone's like, oh, of course, it's obvious. And that's the name of the pattern. I'll just implement it this way. The danger is that comes with a whole lot of loaded assumptions. Now, up until high gear, we're not really looking to use the obvious pattern because we're still kind of trying to build out either some elegance or some understanding about the problem domain. Obvious is going to require a lot of solid domain knowledge or having solved this similar type of problem many times. We often like to jump to it because we're naturally trying to make shortcuts just for efficiencies. That's just how humans operate. So the trick to this is to realize the obvious implementation isn't so obvious. We can easily layer in lots of accidental complexity in solving the problem this way. You can become stuck quickly and frequently, even when solving simple problems. So a better way to think of this pattern is to only follow it if the implementation is trivial, as in like it's so simple. It is truly obvious. Like it doesn't take any explanation. Just that's what it is. That's what it needs to be. If you're struggling with any of these patterns, if you're struggling to apply them, hit reverse gear and try a new pattern. And that leads us to one of the green bar patterns that is not in Kent Beck's book. We call it the backout pattern. It's only ever reused in reverse gear. So you can use reverse in any gear, low, medium, or high. All the gears really dictate are which portions of the principles and practices are you applying, and really how big of steps you're taking. So for example, if I'm writing some code, I'm not always going to use the Fecat approach, the low gear approach, because it's going to take me a long time to get there. I may move to a medium gear and use a triangulation or a one-to-many type pattern, because some of those steps are really trivial and I can quite easily get there. I'm comfortable that if there is an issue, I'll be able to quickly identify where that problem is. So the backout pattern, there's a very specific process I have here in the document regarding how to actually follow it. So revert to a green test run by commenting out your last test, which is failing. Comment out or delete any production code no longer required. I would say comment out versus delete. Now you're in a green state. You should run your test to make sure everything is green. You're happy. Awesome. Then you're going to create a learning test. Now, a learning test is nothing more than a test that isolates that specific bit of code. So maybe you're struggling to calculate prime numbers. Cool. Take out the prime number code, literally plunk it into a new test, and just work with that prime number logic right there. So you're creating a learning test. It's just a special name we give to a test where we're trying to isolate a tricky bit of code. Once you've found the issue with the tricky code, you can now roll that learning back into your code. So uncomment your test, get it to fail, put your learning back in where you were working, where you'd comment out the production code, and you should see it go green. This is, a really great way to isolate the specifics of what's not quite working. Often there's an assumption in there somewhere about the way an API works, or just other things about the problem you're trying to solve, and by isolating that specific little bit of code that's giving you issues, you're able to kind of work through that TDD mentality in one test, kind of iterating through the red cycles until you can get it green. If that's not really going to work for you, then you should drop down into either a Fecat or a triangulation pattern, ensuring that you're taking small steps forward to remove any assumptions or gaps in your knowledge. So really both the learning test and the Fecat or triangulation are about taking smaller steps and rooting out any assumptions. So if you look in the document, there's a section on learning tests. There's some examples. So case 1, struggling to refactor to a generalized solution. And step 2, struggling to get a green test. Case 2. And case 3 is about exploring. I did this when I've written systems. I got a new API. I don't have a clue how it works. First thing I need to figure out is get the auth tokens wired up and working, because it may be using some kind of weird non-standard auth mechanism. Cool, I write a learning test, and I just write the whole guts of what I want to do inside that test. Why? Because it's a scratch pad to explore. And then once I've got that working, I can start pulling out concepts. I'm not trying to make abstractions while I'm still trying to figure out the core essence of the problem. And I think that's really a good point for the exploration case here is, while you're trying to explore, just put it all in one giant method, and then once you can start to tease out concepts and evolve it, you've got both a framework to ensure that it's still working, because you've got a test, and now it allows you to do that refactoring to more generalized concepts. First principles, I don't think I'm going to go through those in detail. So first stands for fast, isolated, repeatable, self-validating, and timely and thorough. Effectively, tests should run quickly. A method should be independent and isolated. That's kind of back to that don't use the test setup and test teardowns, because, well, they can create order of run dependencies. I've often seen this where people, I set it up and then it was all working until I added the 11th test and now things are broken. There's no guarantee run order in a test execution framework, and you're going to often have side effects if you're trying to rely on test setup and teardowns. Each test should be independent and isolated from all other tests, which means it should have the 3 A's, the arrange, the act, the assert sections. Repeatable, it should be able to run 1,000,000 times and give me the same result. Self-validating, I shouldn't have to inspect it. That's what the assertions are for. Thorough and timely, it should cover just about every use case you can think of or every scenario. Don't aim for 100% coverage. That is an absolute silly thing to do. Even where I've had scenarios where I've tried, sometimes it only reports 99.9, even though literally every line's covered. Maybe it's a rounding error or something like that. But regardless, I figure, naturally doing TDD, you're going to end up around 75 to 80% coverage, just naturally. Maybe there's just areas of the system that are really hard to test, you're dealing with the Azure data lake. I don't know how to run even an emulator locally for that. Can stub it up to a point, but sometimes you got to just go, well, there's this ignored test for production issues, and we run it then. Sometimes you just do end up in really funny corners, and there's very little way to work around that. Data Lake's a great example. I'm sure if I put enough effort in, I could probably build a framework, kind of like I did for RabbitMQ in testing. But it hasn't been a big enough thorn in my side where I need a test suite to run on continuous integration. And I often like to use the idea that area of the code is probably going to have low churn. So rather just have a test that needs to be run when changes are made than when every time that a CI build kicks off, because if there's no churn, there's no risk to it breaking. The more code churns, the more likely it is to break, and hence the importance of covering the vast majority of your system with test. Test naming, I think this is a quick one I want to briefly jump into. So I like to take the approach of method name, so what am I testing, underscore given some scenario. So let's say the method's called fizzbuzz from the fizzbuzz karta, the scenario is given a multiple of 3, and then it should be underscore expected result. So in this case, should return fizz. So the full test name would be fizzbuzz, given multiple of 3, should return fizz. So I can read it, I understand what's being tested, I understand the scenario, I understand the expected. Now you'll see variations of this in my code. Maybe I make test fixtures for the method name, and then it's just the given and the should. But generally, you should always try to at least outline the scenario and the expected results somewhere in your test. I should be able to collapse the test body and understand what that test is testing. It can be hard. I get it. Sometimes scenarios or coming up with a succinct result are difficult, but try. And briefly, just so briefly, we're going to touch on the solid principles. I'm just going to give you the one-sentence descriptions. There's a whole lot of text in the document. Single responsibility is the S. A class should have only one reason to change. So really, it should do one thing and one thing well. And if it's not, it probably is at least 2 concepts that you should think about teasing apart. The O, open closed. Software entities, classes, modules, functions, etc. should be open for extension but closed for modification. So you should always favor trying to compose new logic into the system via kind of injecting or decorators or some other kind of design pattern or approach. So I shouldn't really be tinkering with the old code to make new behaviors happen. I should be writing new code and putting a new behavior in. List off substitution principle. Subtypes must be substitutable for their base types. I can tell you right now with most certainty, if you're using inheritance, you'll probably break this. You will likely end up with some method somewhere in that inheritance chain that has a not implemented exception. You've instantly broken this because of that. You cannot substitute A for B because in one case you're going to get a not implemented exception. Not to say inheritance is evil and you should never use it. It's just there's a really restrictive set of cases where it's really useful, and I do mean that. Like generally, always try to favor the composition over inheritance. Allow behaviors to be put into the thing rather than inherited. Inheritance is a bit of a, I guess a good OOP concept gone wrong. It just gets abused so many ways, and it really just makes a lot of headaches, just like that test setup and teardown concept. Interface segregation. Clients should not be forced to depend on methods they do not use. Now you can take this to the extreme and say, I'm going to have one for reading from the database, and one for writing, and one for updating, and one for deleting. But they're all using the same entity. I think that's a little far. I would generally say, if everything's operating on the same kind of entity, they likely belong together. Maybe I could be a little bit better in my interface segregation. There's definitely been times where, at least in a refactor, when I started adding things, I needed to do that, but it's not a step I jump to right away, because, if you start to explode things too far, now you've kind of got this lack of mental clarity. It's really hard to start drawing all the connections between things, and now you're in a state where you're kind of overloading your working memory again because you've got to keep all these moving parts together. So it's a balance, but remember, these are principles. These aren't like set in stone kind of commandments. These are things we strive for. And we tension principles against other principles. You're always trading off one versus the other. So if you favor this one really hard, you're probably going to start having issues elsewhere in the system. And finally, the dependency inversion principle. High-level modules should not depend on low-level modules. Both should depend on abstractions. And when they say abstractions, they're generally meaning interfaces. you know, you shouldn't be newing things up inside a class. You should be using an interface to inject some kind of abstraction around that thing into the class and make it work that way. So that's the end of the video. I thank you so much for listening, and I hope you have a great delivered practice.